Hello IntroStats students, Intro Health Stats students. I thought I'd take this opportunity to just review some of the more important concepts in Chapter 9. My objective is to do this in 10 minutes or less, and it will be a good either introduction or review, depending upon whether or not you have yet to read the chapter in the textbook. So I'm going to try this pen input device as I had before. Please excuse any errors I have with inputs. Let's see, just make sure I have the proper pen here. Okay, looks like I have a red pen. So the first concept is that we're really shifting focus in the class from what I was calling exploratory data analysis or descriptive statistics, and that was chapters 1 through 5, and now we're transitioning into something called inferential statistics. Inferential. Now the difference is described in the second slide in the PowerPoint, but briefly, inferential statistics requires us to adopt some new methods, a lot of them having to do with probability, because we wish to answer specific questions and derive conclusions that apply beyond the sample that we're working with. So given that a lot of this is based upon statements of confidence and probability, Chapter 9 talks about just an introduction to probability concepts. Well, there's a definition of probability, and to make a long story short, it's an expected frequency of an event in an infinite number of trials. So it's not something we could observe, but it's something that we must conceptualize. And the thing about probability is that it's unpredictable in the short run, but it is predictable in the long run. So with that said, we introduced how we work with probability in terms of probability models. So let's just put the word here, models here. And probability models come in two forms. They come in probability models for discrete random variables, that's separate outcomes, and then probability models for continuous outcomes. Now, discrete models are easier to work with, so we usually introduce the concepts in regard to discrete models. And this chapter introduces four basic laws or rules of probability. So the next chapter that we're not going to cover covers some of the more advanced rules. But for the sake of starting the discussion, oops. Not very good with this pen yet. There are four rules, and let's see. The first one, we're using some notation here, so let me talk it out for you. And we say the probability of event A. Event A is anything that's definable in terms of what we'll call later the sample space. It's got to be less than 1, and it's got to be more than 0. Right? So probabilities are restricted to the range of 0 and 1, with 0 representing absolute certainty that something will not occur, and 1 representing absolute certainty that something will occur. And so we have a range of values between 0 and 1. And we often start by considering a 50-50 chance, because that's quite intuitive, which means that 50% of the time we expect something to happen, and the other 50% we expect it not to happen. Right? Then we introduce this idea of a sample space, and the sample space is all the possible outcomes that we're dealing with, and the probability for all the events in the sample space must equal exactly 1. Right? Oops. I don't know what you're seeing, but I'm having some trouble with this pen input device. And then we have a rule for addition of disjoint events, and I'll just introduce that term now. Addition for disjoint events. And the fourth rule or law that we introduce is the law of complements. So if you go through the chapter and or the PowerPoint slides, you'll see each one of these demonstrated. They take a little while to demonstrate, so I'm just going to, oops, looks like I've lost my presentation. Not sure why, so let me go back to it. Okay, seems like I'm now able to resume the slideshow. I don't know what you saw on your screen, but I lost the white screen and went through my individual slides. So with that said, we then, once you get comfortable with this notation, probability of event A, probability of sample space, so on, then we actually start applying some illustrations for both discrete probability models and continuous probability models. So the example used in the PowerPoint slides is a discrete probability model, say where we're defining the event, discrete probability. We used to call it a probability mass, but the textbook calls it a probability model. And it has to follow all the rules up above, all four of those rules. So as an example, I give in the PowerPoints where we let x, so we let x equal the number of female children out of 3, so the couple is planning to have 3 children. So now we can define the sample space as x equals 0 girls, 1 girl, 2 girls, 3 girls. Those are the only possible outcomes in the sample space. And the probability of seeing each one of these outcomes is respectively a 1 in 8 chance that we have 0 females in the 3 siblings, a 3 in 8 chance that we have 1 out of 3, a 3 in 8 chance that we have 2 out of 3, and again a 1 in 8 chance that we have 3 out of 3. Now how this is calculated is not important for now, because we're just going to work with these probability models as opposed to derive them. So that's pretty easy. You know, you can say that what's the probability of seeing 0 or 1 girl out of the 3, and that's 1/8 plus 3/8, or 4/8 1/2, and we can combine these with the law of complement, addition law, and so on. So there are some homework problems having to do with discrete probability models, because those are easiest to demonstrate these rules. Now, the rest of the presentation, or the rest of the PowerPoint presentation, has to do with continuous probability models. And in introductory stat courses, let's see, continuous probability models. And we need to really understand how to use these as a tool. And before we can use them as a tool, we must understand the idea of a density curve, or a density function. And this is a little abstract for some students, but it is nonetheless very important. So we just need to understand some properties of density curves. They're always above the horizontal axis. So I'll just write always above the horizontal axis. And also, let's see, the total area under the curve. So we introduce this acronym, AUC, standing for area under the curve. Has to be equal to exactly 1, because that represents the entire sample space. And finally, the area under the curve in any range then gives us the probability of the event of that range. And we go to some extremes to demonstrate that in the PowerPoint as well as the book. Well, the easiest continuous probability model that we can think of is called the uniform model. And so, for instance, if we have a random number generator, that generates numbers between 0 and 1, and we use as the model a spinner device, say, that has, you spin it, and it can come up anywhere between the numbers 0 and just up to 1, but not well, it does include 1, by the way, so, but we have to put that Oops, that just says 0.75. So if we generate those random numbers between 0 and 1, we get a probability model that looks like a square. It goes from 0 to 1, possible outcomes, and has a height of 1. So the area here is a square 1 by 1, or 1, which is very important when you're dealing with a probability model. Okay, and for instance here, if you want to say what's the probability of seeing a number, say, between 0.5 and 1, that would be have a base of 0.5, because that's 1 minus 0.5 is 0.5, and a height of 1. So when we shade this area in here, that has an area under the curve equal to base times height, or 0.5. So there's a 0.5 probability of seeing numbers between 0.5 and 1. And another example, well, that's enough for now because we don't want to spend too much time. It's explained in greater detail in the PowerPoint presentation. Finally, we introduced the concept that there are many different shapes for density curves. And so a common shape, which we're going to learn about just in our next lecture, is the normal shape. See if I can draw a hefty normal curve freehand. Well, not so good. And we'll learn about this. It's centered on a parameter called mu, which is the mean of the density. And we'll leave that to the next lecture. The important thing to keep in mind is that the area under the curve in any range is equal to the probability of finding a value in that range. I thank you for your attention, and hopefully you'll find a lot of meaning and a lot of beauty in the study of your Introduction to Probability in Chapter 9.